In this problem, we're given a simple harmonic oscillator where the mass attached to the spring is 1.2 kilograms and the spring constant is given to us as 14 newtons per meter. And what we're given in this problem is a little bit unusual. We're told this thing is just whacked with a hammer and it ends up with 0.5 joules of total energy. Now there's two parts to the problem. In the first part, we want the amplitude of the oscillations, and in the second part, the maximum speed of this mass. So each of these is a quick energy conservation problem. In the first part, we can say the total energy in this oscillator, that's 0.5 joules, is completely wrapped up in the spring potential energy if the mass is located at its turning point where it's one amplitude from the equilibrium position. So E is equal to 1/2 Ka squared. That's the spring potential energy if we use a displacement of one amplitude. So we can go ahead and solve this symbolically for the amplitude. And we multiply both sides by 2, divide by K, and square root the result. So this tells us that the amplitude is 2 times the total energy in the oscillator divided by the spring constant, square rooted. Subbing in the numbers, I have 2 times 0.5 divided by 14 newtons per meter for the spring constant, and we take the square root of that. And this gives us 0.267 meters for the amplitude, and it might be nicer to express that in centimeters as 26.7 centimeters. Now in the second part, again, we're just looking at energy conservation here, and we have to think, where is the speed maximum? And this happens at the equilibrium location, where our displacement from equilibrium is 0 and the spring is at its relaxed length, and there's no spring potential energy being stored anymore. That means all the energy, so 100% of this 0.5 joules, is in the kinetic energy of the mass at that special location. And the kinetic energy is 1/2 mv squared. So we can just solve for v at that location, and I really should call that v max. And we do this by multiplying both sides by 2, dividing by m, and square rooting the result. So I end up with the square root of 2e divided by m this time. And now we can sub in our numbers. It's 2 times 0.5 joules up there in the numerator, divided by the mass of this thing, which was given as 1.2 kilograms. And when we run the numbers on this to 3 significant digits, we get 0.913 meters per second. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.